Good morning, everyone. Today we will wrap up. Well, I want to wrap up most of the diode concepts, and then so next week we'll get into different analysis techniques like diode circuits. Today we have a few concepts, pertaining to the junction, PN junction. So let's get into it right away. First up, let's look at the diode characteristic curves. Okay, so here are illustrations of the IV characteristics, whether we call it IV or VI, they will represent the same thing, voltage as a function of current or current as a function of voltage. This right here is the forward bias and the reverse bias. So this is the forward characteristic, this is the reverse characteristic, and this one right here is a zoomed in version. Okay, zoomed in version. So let's take a look at the forward side first. We have a positive voltage that is being applied to the diode. So this is the origin right here, right? Positive voltage applied to the diode, minimal current flow for a while until the junction potential barrier is overcome and the diode starts conducting. And so basically, phi j, which is the built-in potential that that is a result of the depletion region, that needs to be overcome. Until then, the carriers do not have sufficient energy. And once that is overcome, you have a rapid influx of carriers and I'm exaggerating the slope right here. A small increase in the voltage results in a very large increase in the current. Okay. Excuse me. So in the forward region, again, sufficient external voltage must be applied to overcome the built-in potential. For silicon diodes, that potential is 0.6 to 0.7 volts. For germanium diodes, it is 0.2 to 0.3 volts. For gallium arsenide, it is about 1.2 volts. Okay, it is a material property, depends on the element and the compound that we use. Excuse me. And then in the reverse bias, the depletion region width increases and there is absolutely no current flow. And so that is as close to zero as possible. But in reality, there is a very tiny current that does flow due to the minority carriers. We will look at that in the next few slides, but right now, if we zoom into this characteristics, we can see there is a small current that is flowing on the order of like picoamps and femtoamps. And IS is known as the saturation current. Okay, saturation current. Even in the forward bias, you can see in the zoomed in image, this is just a close-up image, the second one, you can see it has, let me write it out, forward and reverse. The characteristic passes through the origin. If diode voltage is zero, the current is zero. But you're seeing some positive value, right? Which is not the case here, right here. And this is something you would have seen in the lab when we did the PSpice simulation of the diode. If we plot the diode current, the y-axis on the log scale, we would have seen something like this. Okay, because in the log scale, there would not be any zero. You would be able to go down to 10 raised to 12, 10 raised to minus 12, 10 raised to minus 15, positive direction, but you'd be able to see this tiny current right here. Okay, and if you didn't do this in the lab, you can still do it anytime, right? You take the first circuit, the first PSpice circuit, single diode, single resistor, just run the simulation from, let's say, -1 to +1 volt, -2 to +1 volt, -3 to +1 volt, and you'll be able to see this kind of current, okay, in the positive side. And you'll also be able to see a reverse current when you zoom into the y-axis. Okay, so typically the diodes will have a forward bias characteristic that looks like this. This is also forward bias. And a reverse bias characteristic that is a very small current. It's almost a flat line, very close to zero. The voltage that is required, to turn the diode on is simply referred to as the turn on voltage, right? That's right here is the turn on voltage. Different authors and different books come up with different terms to refer to these voltages. It is sometimes also referred to as the threshold voltage. And because apparently someone thought it forms like a part of a human leg with a knee, it's also known as the knee voltage. So there are books that refer it to as a knee voltage. All right. But again, keep these terms in mind. We'll refer to this as the turn on voltage, because our book uses that. So, not cause any confusion, I will stick with turn on voltage. Okay, so we have multiple different models, graphical models, mathematical models. So this is the primary equation that describes our diode. And this is basically describing the diode current. Now, depending on how many variables we have, how many terms we have, we are better able to describe our diode conditions. In this case, we have quite a few. So diode current ID is given by the saturation current times the exponent of the diode voltage. Okay, so VD is, of course, diode voltage. Q is one standard charge. T is the temperature in Kelvin. K is the Boltzmann's constant. What else? N, finally N. N describes the non-ideality factor. It's known as the non-ideality factor. And typically, for most silicon diodes, it is usually 1. Most common silicon diodes and most common applications, it's always 1. It's only specialized applications where it might be 1.2 or up to 2. For the most part, it's always 1. So this is one model, one equation that describes the diode current and the diode voltage. It's also referred to as the Shockley equation. For some reason, Jaeger, the author of our book, Professor Jaeger, does not refer Shockley. simply names it diode equation. But if you read a different book and you come across the term Shockley equation, they're talking about the exact same thing. Okay. Now, if you remember, thermal voltage Vt is Kt over Q. So we can reduce the diode equation to Is e raised to Vd over Vt. Right? Thermal voltage Vt is Kt over Q. So Q over Kt is 1 over Vt, thermal voltage. And of course, given a specific temperature, that value for Vt is also a constant, right? Far so good. So what happened? Yes. Yeah. Go ahead. So N is typically taken as 1 for most common diodes and most common applications. And so if you wish to simplify this diode equation, we would simply use the Ns equal to 1. Okay, so the question being asked was, why is N not part of it? N actually is part of it, but typical value is like 1. And so we can reduce and simplify the equation down to simple 3 terms: Is, Vd, and Vt. If we consider the constant temperature, if you're simulating a diode and we say, okay, for the most part, it's going to be at this surrounding temperature, 20 degrees C, 25 degrees C, or whatever value the temperature might be, we can have a fixed value for Vt, the thermal voltage. Then the diode equation reduces even further. You can simply say it is Is e raised to Vd, and then Vt would be a constant. But again, as I said, there are several different models and several different assumptions we can make. We can change, not change, but eliminate some variables depending on our applications. If I wish to do like a quick analysis, sometimes I just take some terms. I wouldn't take everything in there, but that's just me. It wouldn't be the most accurate of answers, but it still works in real life. Okay, so now let's take a look at what happens to the diode of the PN junction under 3 separate conditions: zero bias, reverse bias, and forward bias. Zero bias is something that we saw previously when we first discussed the PN junction, which is right here, right? We have a P-type material, N-type material. We bring it in contact, holes and electrons cross over a little bit, and then a region forms which does not have any free carriers, because the free carriers have migrated away. Because the free carriers are migrated away, they left behind ionized atoms in its place. So you have ionized donor atoms, ionized acceptor atoms in this space. We refer to this as the depletion region. There is no external energy, meaning there is no external bias that is applied. Bias simply means applying DC voltages to your device. So zero bias simply means the state where a PN junction is formed and no external energy is applied. So no external energy source, there's no external voltage. It basically simply is a depletion region that is formed when you create the PN junction diode. Okay. Charge carriers cross over. There is a depletion region that forms. We have a built-in electric field that causes a built-in electric potential, right? That's the built-in potential at the junction. The built-in potential at the junction. And because there are two competing mechanisms of current flow, drift and diffusion, which cancel each other, which balance each other out. We say that the diode is at equilibrium. Okay, barring any temperature changes, we say the diode is at equilibrium or thermal equilibrium. There is no further movement of carriers beyond the creation of the depletion region. Okay, and of course that is formed instantaneously. Remember, we have our fabrication methods, we have our wafer, we implant it with some sort of dopant atoms, and that's it. It forms even before we take the wafer out of our chamber, it's already formed. And that is zero bias. We are not applying any external voltage to our diode. So at equilibrium, the net flow of charge is zero. There is no voltage applied, VD, diode voltage is 0 volts, hence the current is also 0. Okay. So at equilibrium, zero bias, no current flow. No voltage, no current flow. And that would basically be the diodes we have in your lab kits. Okay. Now, it does have built-in potential. So if we do want something to happen, we must apply a external voltage. So let's first apply the voltage in reverse bias, and then we'll look at what happens in forward bias. So in reverse bias, what we are doing is we are taking a voltage source and connecting the negative end to the P-type material and the positive end to the N-type material. What do you think happens in terms of charges? P-type material has an excess of positive charges, N-type material has an excess of negative charges. You have the negative end of the battery connected to P-type. What happens? Opposite charges attract. So we now have holes being attracted to the negative end of the battery or the voltage source, and we have electrons on the other side being attracted to the positive end. And so the depletion, their carriers are moving away from the junction. And so the depletion region width increases. Okay. It's increasing. So depletion region increases. There is no current flow due to the majority carriers. Again, remember, majority carriers are the holes or the positive in the P-type and electrons in the N-type. But there are also minority carriers present in both P and N-type materials. And the minority carriers are of opposite polarity. Remember, minority carriers are of opposite polarity, meaning in a P-type material, minority carriers are electrons, negatively charged, which are connected to the negative end of the voltage source. In the N-type material, minority carriers are the holes, which are connected to the positive end of the battery. And so they are, what are they doing? They are being pushed towards the junction. They're crossing over, and there is a small current that results from the flow of the minority carriers. And that current is known as the saturation current, IS. Okay, that current is known as the saturation current, IS. Now, IS is always present, whether it's forward or whether it's reverse bias. And hence, IS is part of the diode equation. Remember, the diode equation is used for all conditions, right? Forward, reverse, and zero bias. And we will see that on the next slide, the next few slides. So IS is present for forward bias as well as reverse bias. Okay, because the minority carrier motion is always present. So they're always crossing over the junction. And so, because this phenomenon was first observed in reverse bias, it came to be known as the reverse saturation current. But again, that is not technically accurate. Okay, as I said, IS is present in both forward bias and reverse bias. Also not accurate is that it saturates. The reason we name it saturation is because we think that the value would saturate, but it does not actually saturate. Okay, if you increase if the voltage that you're applying in reverse bias, that increase in voltage, that increase in energy is now creating more magnetic carriers to actually, it causes more carriers to cross the junction. And so the saturation current actually increases with increasing voltage. It does not actually saturate. And you can actually simulate this in the PSpice model. If you take that first diode circuit that I just referred to a few minutes ago, and one diode, one resistor, and simulate it from -1 to +1 voltage source, you'll get a current of about 1 picoamp. Okay, you'd have to zoom into the y-axis to actually determine that voltage, but you'll be able to see 1 picoamp, as close to 0 as possible. If you increase the reverse voltage from -2, you would get -2 picoamps. If you go from -3 to +1 volts, you get -3. If you go -5 volts across the diode, you'll get 5 picoamps. And so that reverse saturation current increases with increasing voltage. Okay. All right. Questions? Any questions? Let's take a pause. Questions? Okay. So then let's look at what happens in forward bias. Same thing, but now you have the positive end of the voltage source connected to the p-type where there are holes, and the negative end connected to the n-type where there are electrons. So now they have sufficient energy to actually cross the depletion region. But because there is a built-in potential that is present across that depletion region, a bit amount of the voltage is required, is sufficient before any majority carriers cross over the junction. So majority carriers will be holes on the p-type and electrons in the n-type. They need to have sufficient energy to overcome the depletion region width. And that energy is basically the turn on voltage. Okay, that is the minimum voltage that is required to turn on the voltage. In device physics terms, that's the minimum voltage that is required to impart enough energy to the holes and electrons to cross over the junction. And once that energy is crossed, energy threshold level is crossed, there's a free flow of holes and electrons going in the opposite directions. And so you would have current flow in this direction, going from the anode to the cathode. Remember, first week, we talked about vacuum tubes, vacuum tube diodes, and vacuum tube electrodes. The naming convention was anode and cathode, A and K. That naming convention carried over to the solid state version. We still refer to it as anode and cathode. In a vacuum tube, we have electrons from the cathode that is heated up, apply an energy source, and it speeds the electrons from the cathode to the anode. Current is flowing from the anode to the cathode. Same thing happens here in the solid state version. Current is flowing from the anode to the cathode. Okay. And because the current flow is due to both kinds of carriers, meaning electrons as well as holes, it is also known as the bipolar device. Okay, so the transistor and the diode both are referred to as bipolar devices because the current flow is a result of both electrons and holes. So the depletion region reduces, majority carriers this time cross the depletion region, and it results in a forward current, which of course is indicated by the huge influx, right? That forward bias current. By the way, ID and VD, like any other terms, it's never positive or negative in real terms. It's only for us humans to be able to analyze a circuit and balance out our equations. So anything that is in forward bias, we refer to it as positive. Anything that is in reverse bias, we refer to it as negative. Okay. So if you apply a voltage in the reverse bias, meaning the negative to P and positive to N, it's reverse bias, we assign a minus sign to that quantity. In real life, it's never positive or negative. We never say a battery has minus 5 volts or minus 1.5 volts. You would never say your laptop adapter is minus 50 watts or minus 100 watts. It simply is 50 watts or 100 watts. But if you were to write an equation for your charger, you would assign a negative value to it. Otherwise, our equations would never balance out. Yes. Mm-hmm. Mm-hmm. Yes. Oh, that's a good point. So the point being made was this, because I copied the entire diagram or the illustration over. I was being lazy and didn't want to draw it out again. So I created it once for the reverse bias, and then I copied it 3 times. But yes, that's a good point. Good noticing that. Yes.
So I assume the depletion region goes the other direction as well.
It kind of, well, in the reverse bias, we see the depletion region increases. In forward bias, it does not actually decrease. It's just the carriers have sufficient energy that they can cross over. It does not actually decrease. So I know I wrote down depletion region reduces here, but it in reality actually is that carriers acquire sufficient energy to cross over. Should probably change that. Yes, the effect is that, of course, it reduces, but not, because we do have to provide 0.6 or 0.7 volts to overcome the depletion region width. So let me cross that out. Yes. The 2 arrows, yes. Those are not supposed to be there either. Yeah. All right. Any other questions? Okay. All right. So what happens when, okay, there we go. I was like, what happens when my slide doesn't show up? So we have 3 conditions, right? Reverse bias, zero bias, and forward bias. So what happens to the current ID under each of those conditions? We can reduce the equation for ID into single terms. So if we don't, let's look at zero bias first. We don't apply any voltage. VD is 0. The term raised to E raised to 0 becomes 1 minus 1, hence gives us 0, which makes sense. If diode voltage is 0, then diode current should also be 0, right? If diode voltage is 0, ID is 0. That's the first. The PN junction is at equilibrium. No changes. Then, if you apply a reverse bias, negative voltage, we can reduce this term, the exponent term, to 0. And so that simply gives us minus IS, which is what we would expect based on the discussion we just had. In the reverse bias, there is very minimal current flow, just equal to the saturation current. And of course, we assign a minus sign to it because it's the reverse bias. Yes. We are assuming that we are applying a negative voltage in a large number. So -1, -2, probably not, but approximately like larger than like 10, 20, 15, 10, 20, 30 volts in reverse bias, you would approximately say that it would go to 0. And in the forward bias, we can simply write not be actually 0, it's a negative, and so it'd be a very tiny number. Hence the approximate sign. Does that make sense to everyone? The question being asked was, why does it go to 0? E raised to some negative number. And if that number is large, meaning if the reverse bias voltage is large enough, it'd be as close to 0 as possible. So approximately would be equal to minus IS. In forward bias, same thing happens. N is 1, and Q over KT we can reduce to VT. And so we can simplify this further and state in the forward bias, it will be IS times VD over VT. And these are approximations, obviously. In most cases, if you want to perform a quick analysis, these are very useful. Okay, these are very useful. So we have the equation for the diode current for an applied voltage. We can rearrange the terms to obtain an equation for the diode voltage in terms of the diode current. We just simply move everything on the other side, right? So we have ID divided by IS. Take IS on the other side. Then you take 1 on the other side, so it become +1. And take the log. And then, of course, we have VT multiplied by VT. And we get the diode equation. So VD would be given by VT times log of ID over IS plus 1. It's simply rearranging the terms of the diode equation. We had ID on the left-hand side. We just simply took everything on the other side and VD. So we get everything in terms of VD. Everything else is still the same. ID is the diode current. VT is the thermal voltage. KT over Q. And IS is still the saturation current. If we take the derivative of this equation with respect to temperature, okay, which we see in the next equation. So derivative of the voltage with respect to temperature, we obtain a fixed value of 1.82 millivolts per Kelvin. Okay, so the rate of change of the diode voltage as a function of temperature is 1.82 minus 1.82 millivolts per Kelvin. And this is a very consistent and very linear relationship. Okay, so the diode voltage changes or decreases as the temperature increases. And it's a highly linear relationship. And that was what procedure 3 in the lab was. Okay, so if you procedure 1 and 2 are in the lab manual, 3 was the procedure I wrote out in the lab notebook, and that had to do with simulating the diode voltage as a function of temperature. So you could increase it for one, and if you plotted the graph, you could see that the diode voltage decreased linearly as a function of increasing temperature. And it finds application, and I really like this example, it's in the book, it finds application in digital thermometers. So there are circuits, you take two or more diodes, and you create a circuit in any change in the temperature results in a change in the diode voltage that can be translated to measuring temperature. And so digital thermometers are based on this principle. So the book has an excellent example on how it works. I would say please review or read the example in the book. And I will assign a reading to it anyway. So all right, how much time? 5. So there are two more concepts. One is the reverse breakdown. The other one is the capacitance. So we'll look at both in the last 15 minutes. So the reverse bias, we talked about how the depletion region width increases. So if it increases, it's increasing physically. And because it's doing that, the electric field also increases on both sides of the junction, which results in an increase in the barrier potential right there, VR. And VR is simply the reverse voltage that is applied to the diode. Okay, the reverse voltage that is applied to the diode. So in reverse bias, the VR is added on top of the built-in potential, and the WD0, the depletion region width, increases. Okay. So what if you keep increasing the voltage in the reverse bias? What do you think would happen? We keep increasing, and the electrons and holes are pulled apart and apart and apart, and keep going more and more and more. What happens? At one point, a breakdown occurs, and that is known as the reverse breakdown. Okay, reverse breakdown. And reverse breakdown, there are two mechanisms, Zener and avalanche. And the end result of the breakdown, we refer to it as the junction breakdown. And what happens is a whole lot of carriers now acquire enough energy and result in more carriers being generated to cross the junction. And so a huge amount of current flows in the opposite direction, not in the forward direction, but in the reverse direction, which is indicated right here. Okay. So in the reverse bias, a huge number of carriers acquire enough energy to now freely cross over the junction. Typically, you would say it looks like this. Actually, let's do this. So this is the reverse bias, and the slope is exaggerated. Okay, the slope, it's almost a near straight line like this. It finds useful applications in real life. Okay, in almost a straight line. So for a long time, nothing will happen. This voltage could be very large, 50 volts, 100 volts, 200 volts, 400 volts. Nothing would happen to the diode, depending on how it's manufactured. And then after a certain point, the breakdown effect occurs, and a large number of carriers flow through the junction, and a reverse current results. So let's look at avalanche, then we look at Zener. So in avalanche, what happens is you have these carriers that are freely moving around. Now they have acquired a large amount of energy from the external source. When they acquire this energy, they are now still being scattered and they have energy to move around. And what happens is in their movement in the tightly enclosed space, they run into other particles, they run into other atoms. So let's say one particle or one carrier runs into another atom, it knocks that atom out. knocks other particles loose. So let's say one electron will result in 2 or 3 more electrons being broken out of its bond physically. It knocks it out. And those 2 or 3 atoms in their turn acquire sufficient energy to move around, and they knock a few more electrons loose. So it's a cascading effect where one electron generates multiple electrons. I would say one carrier results in multiple carriers being generated. So it's cascading effect. It's an avalanche effect, and hence the term avalanche breakdown. Okay. So then a large number of free carriers are now present in the device that are now free to conduct electricity. But of course, that happens in the reverse direction. So that is the avalanche effect. And then the Zener effect occurs only in heavily doped. Actually, you know what? Let me write out the avalanche effect. So one carrier generates multiple. And the book actually has a illustration where one particle generates like 2 or 3 particles, and 2 or 3 particles generate. It's like a flow chart, and you can see visually, you can see that avalanche and that cascading effect. Multiple carriers, and so that is the avalanche effect. And the Zener effect occurs in heavily doped diodes. Okay, in heavily doped diodes, the depletion region width is very thin. Depletion width is thin. And so if the depletion region is thin, in the reverse bias, a very small voltage is sometimes sufficient enough to impart them enough energy to cross over the junction. Okay. And typically this occurs, the Zener effect occurs in voltages less than 5.6 volts. Okay. There are diodes that are specifically formulated or created to work in the reverse bias, and they are known as Zener diodes. Okay. And Zener diodes is part of your lab kit. We will perform a procedure in, I want to say lab 4, I believe. We'll perform a procedure using Zener diodes. Now, we talked about reverse breakdown is due to 2 effects, avalanche and Zener. But generally accepted practice over decades, doesn't matter whether it's Zener breakdown or whether it's avalanche breakdown, all of these are just simply referred to as Zener breakdown. Okay, so you have Zener diodes ranging from all the way like few volts, like 2 or 3 volts, going all the way up to a few hundreds volts. You can have Zener diodes even in 1,000 volts. Okay, going on a little bit of tangent, your lab kit has a set of 4 diodes, small black epoxy cylinders with gray bands on them. The gray band indicates the cathode. They are from the 1N4000 series. And at 1N4000 series is exactly the same. So you have 1N4001, 1N4002, 3, 4, 5, 6, 7. So 1 through 7 is the exact same diode. In the forward bias, it works exactly the same. The only difference is that as the number of the diode increases, it reflects the peak reverse voltage or the peak inverse voltage that the diode can withstand. I believe the 4001 can withstand up to 50 volts in reverse bias. And then, 4002 is a little bit higher, 3 is higher than that, going all the way up to 4007, which I believe can withstand up to 400 volts. You could take one of those diodes and stick it in the wall outlet, and it's, it'll still work fine because the inverse voltage capability is very large. So sometimes if you order like a 4001 diode, let's say, from a supplier, if they don't have 4001, they will send you like 4002 or 3, because in forward bias, they work exactly the same. Okay, it's just the reverse bias that is different. Yes. It's doping. Depends on the doping concentration. So if you have a wafer and the silicon wafer that you saw, first of all, like discrete components, there are a few applications we still see discrete components, but it's getting harder and harder to find discrete components manufacturers because it's more expensive. So if you have a silicon wafer, let's say, and you're trying to make a component in there, we can't simply make one diode with a different concentration of the same. Everything has to be exactly the same because you're simply flooding everything together, right? And so if you're making like one diode for, let's say, a lower amount, then there'll be multiple diodes with a lower amount. So one application requires like a simple one, it reduces the cost. So basically, it always ends up being the cost. At our end, as a consumer, it sometimes wouldn't make any sense because if they cost the same as an end consumer, why are they creating? It's a very valid question. Why would they create 4001s? Why not just make everything 4007? Cost. So cost of actually fabricating those would be different. At the end, when they sell them, who knows what kind of pricing they have. Going on a bit of a further tangent, you know how Intel and AMD, they sell their CPUs based on the operating frequency. Like if a 1 gigahertz CPU was be slightly cheaper, then 1.3 would be more expensive, 1.5 is more expensive, so on and so forth. In reality, there's actually no difference. Each CPU is the same as the next one. There's absolutely no difference in the fabrication or anything. They perform tests, and within a certain category, of course. They perform tests and analysis, and if a certain batch of processors can run at like 1 gigahertz, they would sell them at 1 gigahertz. The next batch is the exact same, but they're able to successfully pass the testing at like 1.2, then they will sell them at 1.2. If they can pass the test at 1.5, they would sell them at 1.5. But other than that, there's no difference. Now, if you jump a different architecture, that's completely different. And that's why overclocking is a thing. How many of you have heard of overclocking CPU, right? Overclocking a CPU is when people build their own computers and the motherboard allows them to actually apply a slightly different voltage, apply slightly different parameters, and you can increase the speed of your laptop or your desktop processor. It might make it unstable, which is what happens in the testing units. But that's why it's possible. It's because they're the exact same CPU and there is no fundamental difference in it. Marketing. Anyway, let's come back to our course. I love having discussions, but then we run out of time. I often try to go into tangents and then I have to come back in effort. So good thing is there is no class after this one. So if you have to leave at 10, feel free to leave. Okay. There's only this slide. This is the last slide, but there's at least a 5-minute talk on here. So there's only 2 minutes left. If you need to leave, you can leave. Okay. So if we have, you know what, let me make my job easier. Let me simply copy over the illustration from the other section. What we have here is the top view of our semiconductor PN diode and a 3-dimensional view of the same. Okay. Now, in the top view, we have an N-type silicon wafer, and we are implanting a small area with the P-type material. 2 parallel plates separated by the depletion region forms a capacitance because charge accumulates on either side of the depletion region. This is kind of like the side view. So this is the depletion region, right? This is the depletion region. Charge accumulates on either side. And we say that this diode has capacitance. Okay, this diode has capacitance. So this is inherent property of the diode. Okay, there's also resistance, but we won't talk about this now. Okay, and this is known as the junction capacitance. Let's see right here. So in general, I like to call it depletion region capacitance. It is present in both reverse bias and forward bias. Okay, in the reverse bias, we label it as the junction or the transition capacitance. Our book refers to it as the junction capacitance. And in the forward bias, we have diffusion capacitance. Now, both kinds of capacitances are present in both forward bias and reverse bias. It is just that the effect of one is magnitudes higher than the effect of the other. And so we simply refer to reverse bias as having junction capacitance and forward bias as having diffusion capacitance. Effect is basically the same. In the 3D view, you can see if this is the N-type material and this is the P-type material, we have implanted P-type material into our N-type layer, right? Or it would be N into P, doesn't really matter. And because when you bring it in contact like this, there's a depletion region that develops. The depletion region has a gap. The width of the depletion region is the separation between the plates of the capacitance. And the size of the implant causes the overlap between the PN junction. That is the cross-sectional area of the capacitance. If you remember from circuits 2, capacitance is epsilon A over D. Epsilon is we just referred to it last class, permittivity, and A is the cross-sectional area, D is the distance between the two plates. So if I was to say capacitance of the silicon, for example, would be epsilon S, A would be the cross-sectional area of the PN junction, and then D, of course, is the depletion region width. And because charge accumulates on either side, remember equation for charge, C is equal to, Q is equal to CV. So capacitance is Q over V. It is the ability or the capacity to store charge per voltage applied, per unit of voltage applied, right? Coulombs over volts. So equation for junction capacitance is given here, Cj0 divided by square root of 1 plus VR over phi j. VR is the reverse voltage that is applied, phi j is the built-in potential. Some equations, it is square root. Under some conditions, we can also take the cube root of the denominator. Cj0 is the equation I wrote down on the right. It would be epsilon S times A over WD0. Actually, let me remove this D here and write down WD0, depletion region width. The book rearranges these terms a little bit differently, but it's still the exact same equation. I like this explanation better. Capacitance is epsilon A over D, and so there's no need to separate it out. Cj0 divided by square root. And then in the forward bias, we have the diffusion capacitance. That is a function of the diode current. And tau t is the transit time. The transit time is the minority carrier lifetime. Okay, it's a minority carrier lifetime. And I'll explain what that means. When an electron breaks a bond and moves out, it creates a hole. So this is known as an electron hole pair generation. Okay, electron moves out, generates a hole. This is known as an electron hole pair, and it's known as an electron hole pair generation. As soon as it moves out, another electron might jump into its spot. Electrons have a propensity to do that. So when an electron jumps into an empty spot, that process is known as recombination. And when it recombines, it takes out an electron, it takes out a hole, meaning one negative charge is gone, one positive charge is gone. So the time it takes for a minority carrier to go from an electron in a hole to an occupied spot or recombination is known as a minority carrier lifetime. Because once that minority carrier occupies the hole, it recombines, charges are gone, lifetime is over. And so transit time basically depicts how long a minority carrier will be available. Okay, typically it's less than like femtoseconds, 10 raised to minus 15, 10 raised to minus 16. Okay, so that is the transit time. And then thermal voltage VT and ID, of course, are diode current. Okay, I will assign some reading based on these. And then, of course, quiz as usual on Monday. based on the material that we have covered in this week. There will be a homework assignment over the weekend and a reading assignment, right? So we'll end class here today, and I will see you all on Monday. If you have any questions, I'm available now. I'm available all day until at least 2 o'clock today. And then, of course, over via email over the weekend. Yes, you had a question? CJ0 is the junction is the capacitance at the junction due to the depletion region. So it is the physical is the capacitance due to the physical dimensions of the PN junction. Okay, all right.